So thanks for the introduction, Mark. And hello, everyone. Thank you all for coming out. I'm really glad to be here today to talk to you about the violent and chaotic births of stars. First, I'd like to thank the organizers, students, and large number of volunteers who come together every month to make this possible. So I want to begin by showing you the night sky. If you drive outside the city, you can see something like this. When we look at the night sky, we see thousands of stars. One can't help but wonder, what are these things? Where did they come from? Have they always been there? What happens to stars in the future? Our sun is also a star. Where did that come from? And what is going to happen to our sun in the future? Astronomy as a science is all about finding answers to these kinds of questions. In today's AstroTour, we'll try to answer some of these questions as we embark on a tour through time and space. So let's start close to home and go forward. So let's imagine the future. So about 100 seconds into the future, which amounts to about a minute and a half, I am still going to be talking about this slide. If we add 2 more zeros in 10,000 seconds or a few hours, you'll either be here checking out the various exhibits we have in AstroTours, or you'll be back home dreaming about stars like I do. In a million seconds, or a few weeks, we'll all hopefully be having a great summer. And in 100 million seconds, we'll be in the year 2028 at the Olympic Games in LA, if you're into it. On timescales of a few hundred years, all of us and everyone we know will all be dead. And maybe all humans will be doomed, maybe not, depends on how well we steer ourselves. Now, on timescales of a few thousand years, if humans still exist, maybe we'll have colonies on Mars, or planets in our solar system. And on timescales of a few million years, maybe we'll have a galactic empire. And on timescales of a few billion years, who knows what we'll be up to, what we will be like. But what we do know for a fact is that the Earth and all the other planets in our solar system will still be going around the sun. The timescales at which astronomical bodies form and evolve are so huge. But despite that, and this is the beauty in astronomy and physics, that we are able to predict with a lot of certainty what these astronomical bodies will be doing so far in the future. For example, let's consider our sun. Our sun is so big that its own gravity is trying to crush it. But it is held up in place because at the center of the sun, hydrogen is fused into helium. Now, the burning of hydrogen produces light and energy, which can't. The sun has been doing this for the last 5 billion years. But the sun has a finite amount of mass, or finite amount of fuel to burn. So because of this, about 5 billion years into the future, it is going to run out of hydrogen. And when this happens, the sun will start to fuse helium at its center and hydrogen in a shell. This produces more energy, and the sun will balloon itself. It will also start to get redder. And Mercury and Venus will be engulfed, but it won't quite engulf Earth. But the amount of light that it gives out will be so great that the oceans on Earth would boil off, and life as we know it wouldn't exist anymore. Stars like these are called red giants, and eventually the sun will also run out of helium to burn. And when that happens, the sun will expel its outer layers, and there will be a white dwarf. So this is what happens to our sun and any other star that has the same mass as our sun. Sun-like stars, to summarize, they live for about 10 billion years. But there are stars that we see in the night sky that have more mass than the sun, and some that have less. So what if the sun was less massive than it is now? Or in other words, what happens to a star that is less massive than our sun? And if a star has a mass that is, say, 1/10 the mass of the sun, then it will keep fusing hydrogen into helium for trillions of years, which is greater, much greater than the age of the universe, which is about 15, 14 billion years. Now, this is somewhat counterintuitive because if a star has less mass than the sun, it should have less fuel to burn through. So why does it live so long? That's because stars that are less massive than our sun produce a lot less light than the sun. So they get rid of their fuel very, very slowly. And what happens if the star has more mass than the sun? This is where things start to get more interesting. A massive star, even though it has a lot more mass or a lot more fuel, it burns a lot quicker. For example, a star that has 10 times more mass than the sun burns about 3,000 times brighter. This means that it has a lifetime about 100 times shorter than the sun. And as a result, most massive stars only live for about 4 to 5 million years. In fact, it's somewhere in the region of like 10 to 100 million years for more, or like general massive stars. When they stop burning hydrogen into helium, they also expand like our sun would, and they become red supergiant stars. But they have enough mass that they can keep fusing hydrogen, or keep fusing helium into carbon into even heavier elements, so on until you get to fusing iron. Iron can fuse into anything. That's because it's the most stable element in the periodic table. And so the star, when it gets to the stage, it collapses in on itself and then explodes as a supernova at the end of its life. So here's an animation of what happens to a massive star at the end of its life. It collapses and then bursts. Now, supernova explosion produces so much light that it can outshine an entire galaxy. If there was a supernova explosion within a light year of the Earth, a light year again is the distance that light travels in 1 year. If there was a supernova explosion that close to the Earth, we'd basically see another sun in the sky for about a couple of weeks or so. But there's thankfully no other star that is that close to us, and the closest star is about 4 light years away. So when a massive star explodes, it leaves behind either a neutron star or a black hole at the end of its life, depending on its mass. So here's a summary of the last few slides. So low mass star lives for about 10 billion years or more. Then it burns up in size and becomes a red giant star. Eventually, it sheds its outer layers and leaves behind a white. A massive star, on the other hand, lives for only about 10 to 100 billion years. It then becomes a red supergiant, which eventually explodes as a supernova and leaves behind either a black hole or a neutron star, depending on its size. It is kind of a triumph of 20th century astrophysics that we are able to predict the evolution of stars if we know the initial mass. If we know the initial mass of the star, we can pretty much predict how it's going to live its life. And stars really are the building blocks of our universe. So if we know how stars will evolve, we know how a collection of stars, like star clusters or entire galaxies. Okay, so this was what happens in the future. What happens in the future depends on what happened in the past. So that naturally raises the question, how did the stars get there? And where did the sun? So we can't really go back in time and study the formation of the sun, but we can study stars that are currently forming to understand more about how our sun must have. So let's come back to Earth and then move outwards to explore how new stars. So if you look at the night sky in the northern hemisphere during the winter months, you can see a very distinct and famous constellation. Can anyone tell me what it is and where it is? Orion's belt, yes, that's right. It is, yeah, it is Orion. So you can see it in the top right there. Here are some lines. Now, constellation. So this is the Orion constellation. Constellation is just a bright set of stars in the night sky that we have made up stories about. The stars themselves are not related to each other by any means for the most part. They just happen to look like they're close when you see them in the sky. So here's an illustration of Orion the Hunter. By the way, has anyone ever seen a stellar nursery in the night sky before? So nobody says yes, but you've actually seen, if you've seen Orion before, chances are you've seen a stellar nursery. If you look closely at Orion's sword, you'll see that one of these stars is not in the ellipse. Let's zoom in. So we can see that there's this sort of fuzzy patch here at the center that isn't like the other stars in this picture. In fact, it isn't a star at all. If we have a telescope and a good camera, we can zoom in and see this. And if you have an even better, say we're in space, we can see this is an image taken by the Hubble Space Telescope of a stellar nursery called the Orion Nebula, where baby stars are. It's about 1,300 light years away from us, and it's about 30 to 40 light years away, meaning it takes light 30 to 40 years to cross from one side to the other. It has a mass that is 2,000 times that of our own sun. And what you see here is a huge cloud of gas and dust. The gas here is mostly made out of regular oxygen, but there's also small amounts of other gases like carbon monoxide, ammonia, and hydrogen cyanide, for example. So this is why astronomers call them giant molecular clouds, because the gas here is molecular. Now, I said this is a huge cloud of gas and dust. We looked at gas. The dust in space is very similar to the dust on Earth. It's these very tiny, tiny particles which have a size that is less than the width of our hair. But because of exciting, there being a lot of them, they're very effective in blocking out light from young stars. So this is what the Orion Nebula looks like in visible light, which is all the different wavelengths or colors of light that we can see with our own eyes. Our cameras, however, can see in other wavelengths like the infrared. And this is what the Orion Nebula looks like in infrared. So in the infrared, we see light from baby stars, because dust is not that effective in blocking that kind of light. And you can also see that there are lots of stars left. You can also see there's a massive star here at the center of the bubble. It produces so much light that it can blow away gas and dust. And you may think, how can light? If your light is powerful enough, it can. And in fact, we do this all the time here. Like in medicine, we use lasers for surgeries. Light can push things around. And I should also say, you don't really see this like either of these pictures through your own eyes. Like for example, if you were traveling through one of these, you will see this color. And that is partly because your eyes cannot see the infrared. It's partly because your eyes aren't sensitive enough, meaning they can't really see what it is. And it's partly because astronomers sort of show you these images. So your eyes, here's how they shape. Your eyes can see all kinds of light, visible range. But what they do here is show you light at very specific wavelengths. But just because you cannot see them doesn't mean that it doesn't exist. So if you're traveling in a spaceship, your spaceship could have cameras that see this and show it through your windows. Wouldn't that be so cool? So all that awesomeness is seemingly contained in this small fuzzy patch in the itself. And actually, the Orion Nebula is a very tiny little part of something called the Greater Orion Molecular Cloud Complex, which looks like this. Yes, that is the actual size of this thing in the sky. You need really good cameras that collect enough light to be able to see this. And here's the moon's size in light spectrum. It's about the same size as the Orion Nebula. So this is the Orion Cloud Complex, but it isn't the only nebula you see in the night sky. Let's actually relax for a bit and take a look at some pretty pictures. So here's the star-forming region in the Carina Nebula, which is about 80,000 light years away from us. 15 light years one side to the other. What you're seeing here is big polyps. It would appear that this dust is sort of rising up the steam. But actually, it's the other way around. It's being pushed down. Here's another. This is Roe of Beauty. It's the closest stellar nursery to the world at a distance of about 450 light years away. It's about a light year across, and also, again, a much smaller part of a bigger region. The yellow bits you see here are polycyclic aromatic hydrocarbons. You don't have to know what that means, but it's the kind of dust that comes out of exhaust pipes here. Exhaust pipes of cars. Here's another one called the Tarantula. This star-forming region is not even in our galaxy. It's in one of the Milky Way satellites, large activity. But it's the most active star-forming region in our local galaxies, which makes it appear very bright. It's about 2,000 light years across, which is huge even by gas and space time. At the center, you can see a cluster of newly formed stars going this. Oh. Could I just shout more, like here? You're better now? Okay. Well, okay. So here's a lot. So the columns on these dust columns you see here are nicknamed the pillars of creation. These dust columns are also part of a larger region called the Eagle Nebula. The Eagle Nebula is about 6,000 light years away, and the whole nebula is about 100 light years across. So I think that these star-forming clouds are just the coolest objects in astronomy. And that's not just because they're really pretty to look at, but they literally have a temperature that is minus 250 degrees Celsius. So we've seen these huge clouds of gas and dust, but where do these things come from? What is going on inside them? And this is supposed to be a stellar nursery. So how does that giant molecular cloud convert into that? And for the remainder of the talk, I'll describe the star-forming process, and then at the end, we'll just look at some cool movies. So here's how we think stars form. Say you have some gas in space. Gravity tries to clump matter together. when gas is moving around in space, it tends to organize itself in these sort of filamentary structures because of gravity. It looks very similar to branches on a tree. Here's an example of this seen in the sky. Once again, this is the Orion Nebula, but it's a very small section of it. So then there are regions in these filamentary structures where gas starts to accumulate. And we call these objects cores. Now let's zoom in a bit. So gravity is trying to crush these cores inwards, but they're rotating. So they kind of flatten out a bit. Just like if you would spin a pizza dough fast enough, it will tend to flatten out. So the orange bit you see here is called an accretion disk around the star. Now, this disk is rotating, and the densest material falls inwards and is shown here in red. This is where planets will eventually fall. So this whole thing is spinning, and while it does so, the stuff at the center is still contracting. And as it's contracting further and further, it starts to heat up. Now, the light from this can clear up the gas further out, and you're left with a disk that looks like this. It's now called a protoplanetary disk. And here's an example of something you see on the sky. So now you see these gaps in these rings. These gaps correspond to locations where new planets are forming. These protoplanets, at this stage, they're protoplanets, they puncture gaps in the disk by eating up gas and dust around. Meanwhile, at the center, the star keeps contracting, it keeps heating up, and eventually it heats up to about 1 million degrees and starts to fuse deuterium into helium. And that eventually increases the temperature even more to about 10 million degrees. And when that happens, the protostar starts to fuse hydrogen, then it becomes a star. Now, the star then produces radiation that would heat up the gas around the star. And we get rid of the remaining gas in the disk. Finally, after the radiation from the star clears out the rest of the gas, we're left with a planetary system. So just to summarize this whole thing, we start off in a cloud of gas and dust. Gravity tries to compress it, and you get these filamentary structures appearing. Now, regions in these filamentary structures will start to accumulate more mass and collapse further. These are called cores. These cores are spinning while contracting, flatten out, and turn into a disk. You start to see these gaps in the disk appear, where protoplanets are eating up material, and the star, meanwhile, is collapsing and heating up, and it will then get hot enough to fuse hydrogen into helium. This radiation from the star, or the light from the star, clear out of the gas, and we're left with a young star. So let's have a look at this process in action. So this is a simulation of gas in a box, and this gas is swapping around just like gas cloud in space. And you can sort of start to see these filamentary structures appearing where new stars eventually form. The stars here are represented by blue stars. And you can sort of barely make out that these stars have tiny disks around, which are rotating. Another thing you'll notice here is that stars usually form in bundles. They don't tend to form alone just by themselves. Okay, so let's zoom in on one of these cores. So what you see here is a spherical core that is collapsing and then forming a disk. And the movie that I showed in the previous slide and this one are examples of simulation. And in my research, I try to model the process of star formation on a computer. And that means taking all the physics we know about and then putting it into a code run on a computer. And in astronomy, we usually cannot replicate the conditions in space in a lab. And the timescales for things to evolve are so huge, like see there, it's in millions of years. So we have to rely on using these kinds of simulations as our experiments, where we can test scientific hypotheses and theories to gain insights into the cosmos. You can see here that things start to pop up. There's one little tiny white thing, and there's a couple more. These are actually other stars forming, not planets yet. So I gave you a very simplistic picture earlier. I said that you have one star, planets can form around it. But it turns out that you can also form other stars from the disk. And in fact, you can form many other stars. Our sun is a single star system, but it is somewhat unique in that sense, because most stars have companion stars. And in fact, the most massive stars can even have more than one. And I also should say here that the scale bar that you see here is in AU, which is short for astronomical units. One AU is defined as the distance between the Earth and the Sun. So this is 500 times that. And these simulations, they take a single CPU or a laptop, like the one you may have at home, hundreds of years in human time. But we don't have hundreds of years in our lifetime. So these simulations are run supercomputers instead, which are essentially just big collections of computers, like the one you have. And when you do this in parallel with hundreds of computers, you can reduce the time it takes to run one of these things down to about a month or so, which is much more better for us instead of hundreds of years. So the title of this talk says the violent births of stars. And I basically described how stars evolve, and whatever I described yet about star formation doesn't really seem that violent. So why do I say that? Where is the violence? So here's where violence enters the picture. Newly formed stars can launch powerful jets and winds. These jets are like little burps as the star is accreting or eating material from this. These are like beams of really fast-flowing gas, and the speed at which this material moves usually gets up to like 30 kilometers per second. As this disk is rotating, it's also processing like a gyroscope, if you've ever seen. That makes this very narrow beam wider. And we also see this in the sky too. So here are a couple of images of jets coming out of young stars. New stars also launch stellar winds, which are kind of like this, but more spherical and slow moving. So let's watch this in action. Here's an example from 2 simulations of protostellar jets breaking out. So you have this disk, and then perpendicular with this going out. Okay, so that is violent, but is that it? No, that is not it. If you recall, I said that massive stars produce a lot more light that is enough to push the gas around space. So if you have gas in space that has just formed a massive star, it will give off very energetic in all directions, and the light will start to push the gas. So let's watch a movie of this. Now I'll play this in a second, but let's set the scene. Say you have a bunch of massive stars that are giving out radiation, energetic light. If you're far away from it, it will just look like a slab of light hitting the gas. So here's what it looks like. Now you see here that light will start to poke holes in the gas and dust. And gas that is less dense is blown away more easily. Then we get these sort of structures, which look like something you might have seen before in one of the slides. It is pillars of creation. So these sculptures in space are carved by the radiation or light systems. And perhaps a more accurate name for this should be pillars of destruction, pillars of creation. But the reason they're called pillars of creation is that these pillars can also end up forming stars, because you do have dense gas here. And stars usually form dense gas. Okay, so that is pretty violent, but wait, there's more. So something that I skipped over previously intentionally was the time it takes to form stars. This whole process of star formation takes about 10 to 15 million years. And if you try to recall, massive stars only live for about 10 to 100 million years. They will be formed out of their parent gas cloud and live their lives. And then just a short time later, they're like, all right, I'm and then they go supernova while new stars are still being born. So let's try to put all of this together and watch all the different stages of star formation. So here's some gas in space. Now you may have noticed it looked like a ball. It doesn't really look like a ball. That's just how we set up our simulations. And you can sort of start to see, start to appear. And this is when gravity tries to collapse, moving the mass. Right, there are very dense regions where stars are about to form, and you see these white dots. These are newly forming stars. And they'll start to produce these outflows or jets that stream out of the stars and move the gas. So that was one example. There's one more popping up here. Here. What you'll also start to see are these incredible problems. These are stellar winds that newly formed stars are producing that clear out some of the gas. Looks really pretty, right? And pretty wild too. So you start to see a lot of these stars that are forming right at the center of the cloud. And what you see in just a second is that these stars, these collections of stars, they clear out bubbles. That is because the most massive stars in this cluster have so much light that cleared out the gas. Now, they're at the end of their lives, massive stars, as I said, will go supernova. And you'll see that happen just in a bit. 3, 2, 1, oh. So this is a supernova. Now, this is actually a still in time, so you don't see the gas moving. But if it was moving around, it would just, because of the supernova, the gas would just be expelled really quickly out. It's like a giant explosion. So, okay, are these star forming clouds just randomly present in space? Now, we live in a galaxy. So are there special locations where we see these stars falling in the galaxy? So let's start just by taking a look at a galaxy. So in spiral galaxies, like our own Milky Way, we find that most star-forming clouds lie along the spiral arms of the galaxy. That's because as the galaxy is rotating, it starts to build up material near the spiral arms. It's like a galactic traffic jam. So in this image, you see a spiral galaxy. These purple parts correspond to places where there's a lot of dense gas. The dark regions you see, the dark regions you see are where the dust is. And it's dark because it's blocking out the star from stars. Now we cannot really see how our own Milky Way looks like from this angle. All we see is this. But astronomers can make a map by measuring distances to objects, and the map looks something like this. So you are here about 25,000 light years away from the center of the galaxy. And our galaxy is about 100,000 light years across, one side to the other. It's a spiral galaxy, and it has these many different spiral arms, and we are near one of them. So let's see how things moving now. So on the left is a simulation of a Milky Way-like galaxy that I use in my research. And what I'm showing here is the gas that is present in the galaxy. The yellower the color, the denser the gas, or there's just more gas in the region. You'll also notice that the scale bar here it says 5 kbc, which stands for kiloparsec. And a parsec is a weird unit that astronomers really like. It's roughly 3 light years. So this bar is about 15,000 light years. Now let's zoom in a bit more and see what's really going on in this small patch of the galaxy. So the stuff on your right is just looking at things inside this square on the left. The white and blue dots you see are representing entire clusters of newly formed stars. The blue circles are newly formed star clusters, and as they get older, I just make the color white. And in reality, they don't really vanish, but you'll see here that after a while, the white stars or star clusters start to vanish. That's just because of how I made this movie. Now, what you will notice here after you stare at it for a while is that the blue dots form in regions where gas is very dense. For example, you see this. You see it around. So there's blue stars, newly formed stars forming in that region. And gas in space, that when it gets very dense, we see them as nebulas in our night sky. Then all that gas will eventually end up in stars, star clusters, and then after a little while, the most massive stars have started to die and explode as supernovae. The massive stars then destroy the parent GMC, or the molecular cloud that they formed out of. And the bubbles you see here are carved out by supernova explosions going off. This happens everywhere in the galaxy, and you see these holes as a result, even in this picture. And if many supernovae go off at once, you carve bigger holes in the gas. So let's now try to put everything together. You're the first people to see this movie, apart from me and my friends. This is from one of my simulations that I made just 2 days ago for this talk. Now, maybe you'll see this pop up online in a few months. I don't know. But now I'll play this movie. But what you're seeing here is a portion of a star-forming cloud or star-forming region. And the white dots here represent stars or collections of stars in some cases. And it's a very messy place, as you can see. Let's zoom in now. You can see these sort of filamentary structures here, and that's where stars form. And newly formed stars can often produce these jets and winds. And what you just saw was a shock wave passing through this region. Here's another one. Now, as we're moving away, there's more gas that is in between you and the center of the cloud. So you see a lot more things popping up. This is supernova explosion carving. Now, of course, this is just one star forming region in a spiral arm of a galaxy. And this is just one galaxy in the universe. Now, the universe is so huge, and most of the matter in the universe is dark matter, which we can't really see. But if we could say, it would look something like this. These are the dense regions you see here. Those are places where other galaxies exist. This is also a small patch of the universe. The entire universe is about 10,000 times bigger than this region. This is already 3 million light years. Or this part, 3 million light years. Okay, so let's summarize things now. So here's a summary of the tour that we've been on. We looked at how stars of different kinds or masses live out their lives differently. They form in these things we call giant molecular clouds, which are usually found in the spiral arms of galaxies. Young stars, as they form, produce jets and outflows, and winds, which help to clear out the gas. Massive stars also produce a lot of light, which further clears out the gas and causes these giant cavities that stop. Finally, at the end of their lives, they go supernova, which ultimately destroys them. So that is it. Okay, there's one more thing. Our sun and the earth and you and all of the things you see around you originated in these violent stars.